Okay, last screencast of the unit. I'm sorry I asked you to watch 3 of them today, but you know what? This was gonna go quick, so let's just get on it. We're gonna talk about power, all right? So power is not force, it's not strength. What power means in physics is basically the rate at which work is done, the rate at which an object is gaining or losing energy. We can also think of it in terms of the rate at which energy is transformed from one form to another, say from electrical potential energy in a battery to light or to sound or to kinetic energy. So power is just the rate at which we do work. So, all right. And so we're going to use P to mean power, W to mean work, and delta T to mean time. Now, unfortunately, uh, W is the unit for power, which is a little bit frustrating. So right now, W means work. It's an abbreviation for work, but the units of work is joules. The units for power is the watt, which we use W to mean. I'm sorry about that. Okay. So here you go. 1 watt of power is equal to 1 joule of work done per second, all right? Or 1 joule of energy transformed from one form to another per second. So if I got a light bulb and it says it's a 12-watt light bulb, that means it transforms 12 joules of electrical energy into light and or heat energy every second. That's all it means. It's the rate at which work is being done. 1 watt means 1 joule per second. So let's just try a couple examples and we'll be done. You look in AP Physics 1, we don't even deal with electricity, right? We just deal with mechanical energy. So we're just going to keep it pretty basic here. I'm just going to run through a couple examples and we'll just practice in class tomorrow. So I looked this up. It turns out a Tesla Model 3, which is a pretty cool car, has a mass of 1,600 kilograms. That's mostly battery mass, it turns out. And let's just say it's at rest at a red light. 10 seconds after light turns green, that car is traveling 22 meters per second. It can really do that. What is the power of the car's motor in this case? Well, so the first thing we got to do is we got to figure out how much work was done by the motor. All right. So we're going to say is, all right, the kinetic plus potential, we'll just make it gravitational potential energy plus work initially is going to equal the kinetic plus potential afterwards. Now, we're on level ground. We weren't told otherwise. So we can just forget about this U business. We're not changing potential energy there. Really, it's just about kinetic and work. So we didn't have any kinetic to start with here at a red light. We weren't going up or down a hill, so we didn't have any potential energy, but work was done. Electrical energy was turned into kinetic energy. Here's how much kinetic energy we ended up with: 1/2 of its mass times its velocity squared. Plus, it didn't have any gravitational potential energy. So really, work is just whatever this equals. That's what work is. It turns out that equals 387,200 joules. Okay. Now, power is just the rate at which that work was done, right? Power is just work over time. The work that was done was this many joules of work was done in 10 seconds. So therefore, the power of that was demonstrated by this car would be 38,720 watts of power. All right, let's try this one here. Now I'm kind of proud of this motor I drew here. I don't know why. I just think it looks really slick. Okay, so I got a motor, and it's coming down with a rope, and is attached to this 5 kilogram mass on the ground. Okay, so after the motor in the diagram above has been operating for 12 seconds, the 5 kilogram object is 20 meters above the ground and is traveling upward at 2 meters per second. What's the power of the motor? Now we're going to assume that this is that the Earth is part of our system, so it's gaining potential energy. So as this thing moves up, it's going to gain both potential energy and it's in motion. It's going to have kinetic energy as well. Let's just see what we get here. Okay, so how do we do this? We say, all right, look, the sum of the energies we start with plus work is equal to the sum of the energies we end with. There's no springs involved, so I'm going to leave that out. So kinetic plus potential plus work is going to equal the final kinetic plus potential. Now it's going to have both of these when we're done, but it has neither of those to start with. So I don't have any kinetic sitting on the ground. I don't have any potential. I'm calling this zero potential energy, but work is going to be done by this motor. All right. And what's going to happen is this object is going to end up moving 2 meters per second and has a mass of 5. So that's going to be 1/2 of 5 times 2 squared. All right. So that's going to be 10 joules. Plus, it's going to be a 5 kilogram object. So there's M, there's G, there's H. So that there gives me 1,000. So 1,000 plus 10. So it has 1,000 joules of potential and 10 joules of kinetic. Right. It's not moving very fast. That's how much work was done. Now I just had to divide it by the amount of time it took to do that work, right? So power equals work divided by time. I did 1010 joules worth of work. I did it in 12 seconds. So therefore, its power is 84.2 watts. I think I forgot to mention the time earlier, 12 seconds, okay? Hey, man, that's it, okay? We're done with power. There's not going to be a whole lot of it, but it's just something I do have to cover. There's a couple questions that might come up on the AP test about it, so I didn't want to leave you hanging on that one, okay? So thanks for watching. Sorry to add this third one to your day. I apologize.